Okay guys, what we're gonna do today is we're going to use basically everything that we've been learning in the last few sections and put it all together to analyze the graph of a function. So suppose you have this rational function and you want to analyze it, then the book will offer you or will give you 7 different steps to analyze it. The first one is to find intercepts. So for example, if you would want to find the x-intercept, what you would do, you would set y equals 0 because the x-intercept is those points or those values of x where the graph will intersect the x-axis, and the x-axis, remember, you could write it just as y equals 0, and what you would do then, you'd set let me add a little bit of room there, and you would write 0 equals f of x, but for the function to be equal to 0, the only way that can happen is if the top or the numerator is equal to 0. If the denominator is 0, what you're going to have is going to be a vertical asymptote. And we're going to do those in a little bit. You see my numeration changed. Well, too bad. So at x equals to 2, I have an intercept. So x equals 2, right there, I have an intercept. So I have that information about the graph. So if I want the y-intercept, that one is just 1. You set x equals to 0 and the original function, and you get y equals f of 0, which would be negative 2 divided by 1. If you plug 0 here, you get 0 minus 2, negative 2, and then 0 plus 1 is going to be 1. Negative 2 over 1 is going to be negative 2. So the y-intercept would be at x equals negative 2. So we get that information. You knew how to do that already in college algebra perhaps, or a similar course. So there's nothing new this far. Now, vertical asymptotes. Well, for a vertical asymptote, what you want to find out is when the denominator will be 0, and for a rational function, that is. So you have x plus 1 equals 0, and then you subtract 1 on both sides, and you get that x is going to be negative 1. So at x equals negative 1, we have a vertical asymptote. So my line x equals negative 1 is this one right here. Anyways, that right there, okay? So now we need a horizontal asymptote. And here we have to look at the degrees of the numerator and the denominator. If the degree of the numerator and the denominator are equal, then you have a horizontal asymptote at y equals the ratio of the coefficients in front of the x with the largest coefficient. So in this case, you would have limit as x goes to positive or negative infinity, but in this case, both limits are the same. And the limit is going to be the ratio of the coefficients, which is 1. If you had that the degree of the numerator is larger than the denominator, then you wouldn't have a horizontal asymptote, you would have a slant asymptote as we did in the previous video. And if the degree of the numerator is smaller than the denominator, so the top is the degree is smaller than the bottom, then you have that the horizontal asymptote is just 0. But in this case, it's just y equals 1, which is the line right here, like there. And that gives us our vertical and horizontal asymptotes. I should draw a little bit more. I know it's crooked, but at least just so we see where the function should go. Alright, so the domain of the function, then in this case, domain of the function is just all those, the set of x's such that the denominator is non-zero. So basically all the x's that are not equal to -1. So you could write it as the interval between -infinity and -1 open, and then from -1 to +infinity. So that would be your domain. So the function is defined for all those values. Let me add some room here. Oh, well, I added it on top, it's okay. Now the derivative. I will need more room for that, so let me add a little bit more. So the derivative here is going to be equal to, well, you have a quotient, so you have to do quotient rule. So derivative of the top, or the numerator, is 1 times the bottom, sorry, minus the bottom, the top, sorry, times the derivative of the bottom, which is 1, all over the bottom squared. Let me redraw that. And then you just simplify, and you would have here x minus x, all the x's go away, and then 1 minus -2, so it's going to be 1 plus 2, which is 3 over x plus 1 squared. Let's write f prime again. Alright, so you have your derivative there. That's good. Then we're asked to find the critical values. And somehow my image got all messed up. Somehow I don't really know what happened, but you see these points right here when I scrolled. Sorry about that, I may be giving you a headache here. This points got shifted. This was supposed to be y equals to 1, and now it's at -6. So let me redraw those. Somehow it all got messed up, so let me redraw them where they're supposed to go. So x-intercept we said was x equals to 2, so it was here, and the y-intercept was y equals -2. And then at y equals 1, I had my horizontal asymptote. And let's hope that this doesn't get moved. Alright. And the y equals 0 was up here. Somehow, I guess when I gave myself more room, things got shifted. So let me try not to do that. So critical values. Now, critical values, remember, are those where the derivative is either 0 or undefined. Well, if you set this equal to 0, you'll find that this has no solution, because you would have 3 over x plus 1 squared equals 0. That cannot ever be 0. So there will not be value of x that makes f prime equal to 0. Now, there is a value of x that makes f prime equal to be undefined, but that is not going to be in the domain of the function, which is the value of x equals -1. So we had that asymptote, we had a vertical asymptote there. So that one is, there's no point for the function, therefore is not we don't have a critical point there because the function is simply not defined. Okay, so since we have now to look at increasing and decreasing, the intervals we're going to grab are going to be from -infinity to -1, and then from -1 to +infinity. So we have the exact same intervals as the domain. We would add more intervals if, for example, we had a critical point. But since we don't have anything else other than the vertical asymptote, we don't add anything. So here we choose a test value, and put -2 and 0, and look at the sign of the first derivative. So when you look at the first derivative here, the first derivative will, so long the denominator is not 0, it's always going to be positive, because you will have a number that is going to be squared, and if this is a non-zero number, then it's going to be positive, and then you have a positive number divided by a positive number, so this is always going to actually be positive. You can plug it in and find out what value you get, but it's going to be positive. And when you have that, then you have that the function is increasing on both intervals. So the function is always increasing then. Now for inflection points, what you would want to do is find the second derivative, and remember that is going to be the derivative of our first derivative. Let me see if I can fit everything in the same screen. Yes, I can. So right here I have the derivative, and what I'm going to do is I'm going to write it as 3 times x to the x plus 1 to the negative 2. Why do I do that? Well, because now if I want to take the derivative of this, I can just apply chain rule instead of doing a quotient rule, and that's a lot easier. So the derivative, if you want, I can write it right here, just so we can see it on the same screen, and it would be negative 2 times 3, so negative 6, and then x plus 1 to the negative 2 minus 1, so negative 3, times the derivative of the inside, but the derivative of the inside is just 1. So you could write this as negative 6 over x plus 1 cubed. Okay, so for inflection points, you would want to find those points where the function, the second derivative is 0. And so let me copy it again. Let's see, yes. So in that case, there are no inflection points again. So for concavity, you would have to use the same intervals we use for increasing, decreasing. Oops, that came too close. There you go. So from negative infinity to negative 1, and then from negative 1 to positive infinity, and you get your test values, negative 2 and 0. And you look at the sign now of the second derivative. And in this case, since we have a cube in the denominator, then there will be a change of signs. So when you plug negative 2 in here, this becomes negative 1. Cube is still negative, and then you have a negative, and so the concavity is going to be concave up. And then when you plug 0 here, you would have 1, that would be positive, and so negative divided by positive would be negative, and your function would be concave down. Well, if we put everything together, I have here a graph of the picture of the graph of the function, but let's put everything together as we had. The function has to always be increasing and asymptotic to these two lines. So I could have the function go here. Now you know the answer because I didn't erase the function I drew on the computer. So the function could go there, let's say more like that, or it could go down here. But now here the function would be decreasing, and what I found from my table is that the function is always increasing. So this bottom one cannot be. So to be asymptotic to those two lines, you only had those two options, and it must be then the top one. Now to be asymptotic to these two lines and crossing this point, well, certainly the only option is this. And you see how if you choose that part, the function continues to be increasing, and so it matches what we found, and then the function goes from being concave up to concave down, just as we had found in the concavity table. So it's basically the same thing we had done before, we're just putting it all together.